funded by a variety of sources, including the National Science Foundation, DARPA, AFRL, NIST, and a variety of industrial sponsors. He has received several Best Paper Awards, including and nominations, including just within the last year from ICCAD and ICDM. He served on many conference committees, including recently General Chair and Technical Co-Chair of GLS VLSI in the last 2 years. And he's also an Associate Editor for the IEEE Transactions on VLSI Systems. So please join me in welcoming Professor Homayoun.
Hello, everyone. Thank you so much for the organizer of this event to give me and also my team the opportunity to present our work on hardware cybersecurity. And we have a very diverse department, diverse research background. We have a strong team in computer engineering, signal and system, device, and many others. And I'm just one faculty out of many active faculty who are doing a lot of. It's not on. Okay, great. Okay, hopefully it's better now. The work that actually I'm going to present today is about hardware cybersecurity. Many of you have heard of the word security. You're dealing with on a daily basis. You're hearing the news of various attacks that are happening in essentially on a daily basis. Companies are reporting it, and it's affecting essentially our life. Today, I'm going a new aspect of cybersecurity, which is hardware security. And it is a relatively new field, a lot of opportunity for research for us in academia, and also a lot of also interesting problem to solve and address both in academia as well as in industry. So first, let me actually acknowledge the excellent work of my team, the student who work hard, and essentially today I'm presenting their work on their behalf. These are several students that have been involved in research over the past 2 years. I used to work in university, George Mason University in Washington, D.C. area, and then recently moved to UC Davis. Some of these students are still with me. Some of them graduated. We had team that work on auto-tuning big data frameworks. This is a big problem that industry is dealing with. When you submit your application to cloud, how you can tune them or auto-tune them as an end user. You should not care about how to tune various performance knobs, but it seems that they're really important from performance, power consumption, as well as the cost for the end user. So we're trying to come up with a solution to auto-tune them without really involving the end user. We had another team, still one member left, that are working on accelerating machine learning application. And this is a problem that industry has been dealing with for the past several years. We have an alternative solution to some of other research work in university, work funded by NSF, Intel, as well as Xilinx. We have groups that are working on hardware security, doing reverse engineering, which is going to be the focus of most of my talk today. And finally, a group that working on architecture and system level security. Some of the new attacks that you may have heard of recently, such as a Spectre and Meltdown, reported by industry. We actually have been funded to work on these attacks since 2016, that these attacks even have not been really introduced in a wide market and also academic domain. That research essentially has been funded by DARPA. We're still working very closely with the Defense Advanced Research on the project. So the lab actually has been really active in producing human resources for industry and also academia. Here are just 10 members of the lab that graduated in recent years, in the past 2 years, and joined academia as well as industry. And most of them are working in cybersecurity related field. We have faculty that also, one of my students recently joined UC System, and essentially another student of mine joined George Mason University. So the lab is active, working on a lot of cool projects. project within industry as well as with government to essentially address real life problem. And that essentially help also our student to get attracted and get absorbed to the market fairly quickly. So having said that, let me give you an overview of some of the projects that we've been doing in past several years. And the main two topics of the labs are energy efficient computing as well as high hardware cybersecurity. So on the energy efficient computing, one of the very first projects that we've been involved working was developing an ultrasound prosthetic arm to essentially for amputees. Traditionally, people been using EMG method to control prosthetic arm, but that has some or essentially many problem in terms of the accuracy, in terms of the controllability, and the alternative solution that one of my colleagues proposed was to use ultrasound band. So essentially, we attach this ultrasound band around the hands of amputee. We collect signal in real time. We translate them into various domain, and then finally we extract pattern. We extract pattern, and my team contribution in the project was essentially to do the acceleration. We started with using some GPU, Tegra GPU, many of you have heard of it, but apparently that's not really sufficient, and we moved to FPGA-based platform to improve the performance, eventually making it real time. And here essentially is a simple video showing how this is done. Oops. So this is the hand of amputee, and we connect it through ultrasound and oops. So that can be controlled. So sorry for the audio problem. But another project that we've been involved with was accelerating image processing application and essentially using heterogeneous platform. This is an area started about 2010-11 in industry as well as in academia to how we can essentially improve the performance of some of these data-intensive, compute-intensive applications. And we started looking at some simple platform such as the Xilinx board and these are Zinc board, to understand how with this simple Zinc board we can improve the performance of some of the sophisticated data-intensive application and match the performance of what we gain in essentially a data center or high-performance computing center. And it turns out that with this FPGA platform, if we program them efficiently, if we offload the right type of job to this FPGA platform, by managing them efficiently, we should be able to gain significant performance benefit and can match the performance that we gain on a server. And essentially our results show that with just stacking 3 Xilinx Z board, these are $70 each, we can match the performance of a 6-node server when it comes to running. We tried it with Hadoop MapReduce, later on we tried with Spark, but as long as we make sure that the application is in a custom manner mapped to the FPGA efficiently, we should be able to match the performance, which is significant gain from, again, cost perspective. So another type set of work we had was auto-tuning big data application. This is also a challenging problem when, as an end user, you submit your job to Amazon, AWS, or other cloud platform. At the end, what is important for the user is cost. And what we know from computer architecture perspective is tuning these parameter, the application parameter, system parameter, would impact the performance as well as the power consumption. And as an end user, this is something most of us really don't care and should not care. If we can design a system, a sort of a hypervisor in this case, or a scheduler that can identify what are the important parameters that in terms of the cost, in terms of the performance, in terms of power consumption, we can potentially find the right corner spot to give us the maximum performance at the lowest possible cost for the end user. So this is essentially another type of work that is sponsored by National Science Foundation, and we publish several cool research on this. these are all the work on energy efficient computing track of the lab. On the hardware cybersecurity, the very first project that we work on was with General Motors, and essentially they provided us with a multimedia system for GM 2013-14 car, and they want us to hack into the system without any sharing any knowledge, any technical report, anything else from GM side. And as you can see in this case, we were able to hack through the multimedia system from the through the Bluetooth. Here we put the George Mason University logo on this system, and just to show what kind of vulnerability exists in the system, and to report them to the company for potential mitigation technique. Also, another project is on protecting against software-assisted hardware attacks. This project funded by Defense Advanced Research Agency is still ongoing, and I'm going to talk about this extensively as well today. So that essentially brings me to the rest of my talk today, or the main topic. The outline of rest of my talk is, first I'm going to talk about hardware security field in the past, what this field was about, what the current state is about, and what is going to be about in future. Then I'm going to show you a video which, in my opinion, best convince people that this is real. The field is real. This is not just some imaginary problem that people in academia came up with to publish paper and then move on. Finally, I'm going to present some of our recent work on the topic, funded by various research agency, and what we're also doing currently and going forward. So let's first see what the hardware security field is about. Hardware security is, with a different name, maybe crypto engineering or cryptography, many of you have heard of it, is not necessarily a new area. Crypto engineering has been around for many years. In fact, if you look at the history, ancient Egyptians were using it for amusement. The ancient Greek were using eskytale. This was essentially they put this around the rod, the parchment around the rod, and by using the rod, they would encrypt and decrypt the message to send it during the wartime. And also in recent history, more recent history, Enigma machine. You've seen the movie also. This is being used for cryptography and for encrypting decrypting message. So the field with that particular essentially title, mission to encrypt decrypt message has been around for many years. However, in recent years, the state of the field has changed significantly. In fact, in today, we are building computer and in a different manner. This is more sophisticated. It has multi-layer from the software, architecture, hardware, application level. There are multiple layers involved in building a computer. And security essentially built as a multi-layer foundation across all of its stack. And at the bottom layer, we have hardware security. On top, we have operating system, network, transport, encryption, software, as well as app. So the fact that if we have security at all level above, if we don't have it at hardware level, create a problem. Because if you don't trust the hardware, no matter how much security you have at the higher level, you won't be able to run your application safely and confidently. So this explains why looking at the security problem at a hardware level is important, besides addressing the problem at other layer. In addition, today the way we design IC, when I say today, perhaps since several years ago, it really changes significantly. In fact, today there are several steps involved in designing and manufacturing IC. We start from the design house. The design house essentially creates a design with their various vendors that they contribute IP. Then we essentially go through various phases of design, including verification, placement and routing, front-end design, back-end design, all the way to creating a GDS2, sending it then to the foundry, which the foundry could sit somewhere else on the globe. And once the IC fabricated, then the design will come back. We need to perform the testing, verification, and the fact that there are several steps involved in this design, just making it the design of the IC insecure by nature. Because it's being done by different player, and these players are sitting across the globe. and we don't have control necessarily over them. There could be in different jurisdiction, legal jurisdiction, and potentially their problem. So this is a little bit slow, and okay. So why hardware security today? In fact, today the ICs are more complex, they're more heterogeneous, they're more diverse. We are essentially integrating various IP from different vendors. Can we trust them? Obviously, we can, but we have to also verify. We have to verify, make sure that they don't really put Trojan or some malicious hardware on the design. So this is how today design are different from what we had in the past. In addition, in the past, IC design, fabrication, everything used to take place in one location. But today, this is different. It is not really happening in one location. The design house could be in California. Some IP, we could get it from another part of the globe in Asia. We fabricate it in Europe. So the fact that the foundry itself also is expensive. Running a foundry could cost somewhere between $5 to $10 billion, and not necessarily state of the art, exacerbate the whole situation. That now we design something, but someone else sitting somewhere else around the world is fabricating our design. Can we trust it? Again, that's a big question that we need to answer. And because of all these cost-related problems, globalization, the result is many companies in the US and across the globe, such as AMD, Avago, Marvell, NVIDIA, Qualcomm, they become fabless. They don't run their own foundry. They rely on third party. Also, many small companies, not only they can't afford their foundry, but they also cannot have their own IP. They're using third-party IP. So the problem essentially is at multi-level. This is an example of a global foundry map, but we have today. One of my students essentially helped me collect this data from online sources. We have very few left in US. Again, Intel also is a big player. A lot of them essentially move already to Asia. One of the latest one, not so latest, essentially almost 2 years old, that was part of the IBM, not anymore IBM. It was acquired, and they're still working with the government, supplying some of the fabricating some of the IP they had. But this is going to be a problem also in future for the government as well as the industry. So what we can see is that clearly there is a big shift moving from or leaving some of this foundry leaving US to other countries, Europe as well as Asia. There is a website called SourceMap, and actually you can go to that website and type in your digital device information. And it doesn't have necessarily a complete database, but to a good extent, for a lot of device, it can tell you for the device that is designed in California, let's say Apple, in this case I put Apple iPhone, one of these earlier version, 5, 6. I believe the design is in California, but you can see the test, the integration, the fabrication, everything else is done across the globe. So you can see that while this device was designed here, but there has been a lot of players across the globe that working together to bring this device to the end customer. And because, as I said, they're located across the globe, potentially we cannot trust them, and we should also verify what they do with our design. So because of this globalization, untrusted offshore entity, in this case are limited to foundry, they can potentially insert Trojan in the design. They can overproduce the intellectual property. They can reverse engineer the design, as well as they can perform counterfeiting. And all of them are essentially catastrophic because they're happening at the hardware level. And at the software level, while you can run a software, can tell you that your running application is potentially a malware, it's still your information, but you can change a lot of things. You can maybe discover it, and you can mitigate essentially the problem. But at the hardware level, it's really sophisticated. There are few transistors in a billion transistors. The question is that how we can detect them. Can an end user detect them? So there are a lot of challenging problems that needs to be addressed, and that's why this area is becoming more and more important given the challenge and the trend that we are observing. So let's take a look at and see where the source of threat could be. Looking back at the standard design flow from the design house all the way to the PCB assembly, the hardware Trojan can happen in these three places. The overproduction and IP theft can happen in foundry, SoC integrator, reverse engineering in foundry all the way to the test facility, counterfeiting in foundry all the way to the test facility. So essentially, the problem could be almost everywhere in the design, outside of the design house, either at the test facility or at the integration facility or even at the IP facility, the facility that provide third-party IP to the company. So everything I discussed today looks a really interesting problem to address. But first, let's see if this is a real problem. And to best convince you that this is a real problem, as I said, I thought the best would be to provide you a video that one of my Java program managers shared it during a meeting. It belonged to public domain, and it's essentially a report by CNN. And you can even YouTube it.
These may look like the real thing, but deep inside some of the U.S. military's most sensitive equipment are counterfeit electronic parts. A congressional review of just a sample of the defense industry supply chain found about 1 million bogus components.
We cannot allow our national security to depend on electronic scrap salvaged from trash heaps.
And they were found in critical equipment. On a U.S. Navy anti-sub helicopter, the night vision and targeting system contained a counterfeit transistor. Its failure could have compromised the pilot's ability to identify targets. On the C-27J military aircraft, suspected counterfeit memory chips were discovered. And on the P-8A Poseidon airplane, an ice detection module had fallen out of its socket, a part that on closer inspection appeared to be a fake. A Government Accountability Office investigation found that many of the counterfeit electronic parts can be bought on the internet.
We consider the problem itself to be a very serious one, possibly affecting the lives of our military personnel and the capability.
So there's a longer version available online on YouTube, and I encourage you to watch it online. It's very interesting, a lot of interesting information shared there. And this is essentially a 2000, I believe, 13 or 14 video. And it started from military equipment, and imagine if that can be penetrated into military equipment, it can also, the problem could exist in commercial devices, which they don't have necessarily security at that level. And the companies, in general, they don't sell security products. So security for them is not necessarily a big concern unless there's a problem. Companies sell performance, companies sell power consumption, companies sell application, but there are not many companies across the globe that sell security. For them, or the past at least many years, security has not been a main concern at this level, at the hardware. And the problem is starting to emerge in even the commercial market. So we actually propose several solutions to defense industry, and we work with several companies as part of our DAR project. Today I'm going to present one of the main ones, which we recently also had a test chip tape out to harden RISC-V architecture, which many of you have heard of it. The solution essentially is lookup table-based obfuscation, or we call it design obfuscation or logic obfuscation. And this is a very simple solution to be integrated in current standard design flow. And this is essentially the beauty of it. So before giving any information about what the technique is about, let's first look at how the reverse engineering is happening on an IC, because that really helps us to understand how a Trojan insertion or IP cloning or counterfeiting can also take place. If a company can do reverse engineering, if a third party can do reverse engineering and can understand what your netlist, what your design is exactly about, they potentially can identify vulnerabilities and insert Trojan there, or overproduce it, or program it, or reprogram it, and can do many harm. So reverse engineering is essentially at the core of all of this problem. Very similar to design automation conferences like we have, companies like we have Cadence and Synopsys. In this field, there are several players, but two of the important ones are ChipWorks and TextPlane. that they are in the business of reverse engineering design. You send your design, they charge you essentially some amount, and within few weeks they give you the net list. And the two companies actually have been working also in litigation among companies, Broadcom fighting Qualcomm. They hire one of this company to show that one or the other really violate the IP. So they're also doing, they've been in this business for many years. The process is very similar to design automation, where we do front-end design, placement, routing, all the way to the back-end, but reverse. We start from the packaging or the packaging. We need to remove the package. How they do it, they use some nitric acid, or they use CNC machine, they remove the package, they go to the silicon layer. Then they essentially can remove metal after one another. They take image all the way, starting from RDL, redistribution layer, metal 12, metal 11, all the way to metal 1, and then they go to the silicon layer. And once we are in silicon layer, we can see the net list, the interconnect, we can get it from all these metal connection. They are using essentially SEM camera. This camera essentially give you high resolution also. Once they collect all these image at a very high resolution, they need to label them. They identify where is the memory, where is the processor component, where is the input, where is the output, and where is the crypto engine, and so on and so forth. Once they identify each of them, then they're using some image processing software to process the attached image. Once they collect all these images, they attach them, they form a larger image. They use image processing software. Then image processing software from these SEM collected images would tell you what the net list essentially would look like. And while this part seems to be really sophisticated, we are essentially able to reproduce this in the lab in a matter of 2 to 3 weeks. And just to give you a hint why this is really simple, this is a simple image processing. It's convolution neural network based. We have a lot of sophisticated convolution neural network based image classification method available out there. The sort of application that here we're trying to train the network is really simple. It's not a random image. The layout of the design, an AND gate, NAND gate, NOR gate, or the database is very small, maybe 100, 200 type of objects we have there. Once we train it, we are able to essentially reproduce the image quickly and very fast. So this is essentially the figure here, show the taxonomy of the field. Essentially, we call it reverse engineering, hardware obfuscation, camouflaging, a lot of terminology we're using. Attack essentially on the hardware using reverse engineering. When the field started in about 2009, infant research started from UCLA. Obviously, there hasn't been a lot of research there wasn't a lot of research back then. Several ideas was proposed, but within very short amount of time, for a solution to protect IC back then, an attack solution was proposed that could essentially defeat the prevention mechanism. And as you can see, for every defense mechanism that was proposed to protect your IC against reverse engineering, within a matter of few months, 6 months, an attack mechanism was proposed. The one that I highlighted in red are our recent work, which actually we did also taped out fabrication on the recent one. But what actually tells us is that this is a serious problem. No matter what kind of solution we propose, almost in a matter of 6 months, there is an attack. But the good news for us in academia is that there's always a problem for us to look at and to solve. So the solution actually that we propose, which is relatively simple, and the most important thing is that it also can be integrated with the standard design flow. It's not disruptive to standard design flow. You can have the best solution, but if it's so complicated, it's not integrated in the standard design flow. You take it and you go and talk with folks at Intel, in global foundries, elsewhere. The solution might look beautiful on paper, but they're not necessarily going to adopt it because it could disrupt their design flow. For them, it's important that the design flow stays the same. The solution minimally add additional step in their already sophisticated design flow. So that's why we choose lookup table-based obfuscation. And the idea is very simple. I essentially explained the idea through this simple example. We have this number of gates in the design, and we identify several of them, and we replace them with lookup table. What is lookup table? Lookup table is the foundation of FPGA. That's why you can do programming. You can program the FPGA. So we replace part of the design with lookup table. Once we replace them, then the attacker, when they do reverse engineering, what they see is simply a bunch of gates that are lookup table. They are programmable. So obviously it would be difficult. However, there are a lot of attacks that develop since the time that we propose a solution using satisfiability modulo theory, SAT attack on the theory base, that they were able to detect this. I'm going to explain what is our solution to that as well. But first, let's see why making the design reconfigurable make it difficult. If we have a two-input lookup table, then the attacker would obviously guess the two-input lookup table, the number of possibilities are limited, 2 to power to 2 power to 2. We have 16 number of possibility, AND gate, NAND gate, a couple of combinational gate, and the attacker can try it for each of them, a combination of them in a brute force manner, and potentially can guess. But the problem for the attacker happens when the number of input to the lookup table or the number of programming bits increases just a little bit, from 2 to 3, 3 to 4, 4 to 5. Incrementally increase in number of programmable bits on the lookup table would make this problem exponentially difficult from the attacker perspective. And the reason is simple. So if you have n input lookup table, the number of possibilities is 2 to power to 2 power to n, meaning that the attacker for each of them needs to try this many. Just to give you how big that number could be when we have 10 input lookup table, this is essentially equivalent to centillion for 10 input lookup table, meaning that for each of them, the attacker needs to try 1 followed by 300,030 number of possibility for each of them in a brute force manner to find out what functionality they carry, which is almost impossible. And multiply them together, even the problem could exacerbate. So any solution we come up in this field, in this area, need to address several challenges. Here I'm actually just listing some important ones. First, the solution has to be manufacturable. We should be able to design it. The solution has to be competitive with ASIC CMOS. This is really important. Also, it should not be disruptive to standard design flow, compatible with CMOS as well. It should be secure. It should not be reverse engineered. And most importantly, the programmable bit should not be accessible. We cannot make this design just CMOS-based, store the lookup table in a third-party memory, because then we make that third-party memory a source of attack and vulnerability. The attacker then don't need to attack our lookup table inside the chip. They simply can attack a memory that is stored off-chip or even on-chip. And by reading the bit, they can reverse engineer the design. So for that reason, we are relying on MTJ-based lookup table, non-volatile base. We also use eFuse base as well in our recent tape-out. So MTJ, essentially, again, there's not much time to go over the detail, but using non-volatile based lookup table, we are able to store single programmable bit on the same die that we are storing the AND gate, NAND gate, NOR gate. And this is a lot of reconfigurability at a very fine grain. But the good thing is that we don't need to do it everywhere in the design. We don't need to make the entire design programmable, just a little bit. And this is what I'm going to talk about later. So we develop a lot of circuit solution, and to realize it, we introduce several standard design flow. But the one that we recently taped out is fully synthesizable lookup table and can be integrated with the rest. Is introduced as a new essential module in the library. You have AND gate, NAND gate, NOR gate, and you also have added lookup table. So your synthesizer can go and choose between AND gate, NAND gate, NOR gate, and lookup table to do the synthesis, front end all the way to the back end. So that way we are not really disrupting the standard design flow. Looking at the result of area and delay and power consumption obviously show some challenge to be addressed, meaning that the area, delay, and performance of lookup table are much higher, so they have to be addressed. And this is what our replacement policy, the policy that look at where to insert this lookup table in this multi-million gate design, is looking to minimize the complexity. So the standard design flow that we propose is not really interrupting what we currently have in place. We do RTL logic synthesis all the way to the GDS2. We essentially add additional step here, and we perform everything else as we used to. In the front end, we do lookup table-based searching in the design, multi-billion transistor design, where to find gate to replace it with lookup table. And we replace them, we do the resynthesis and do the timing to make sure that the timing hasn't been missed, and we do it multiple times until the timing is satisfied. So essentially we are relying on also the tool from major vendors, Synopsys, Cadence, Mentor Graphics, to do us a timing here without really disrupting the timing, and as well as the power analysis, as well as the area analysis, and so on and so forth. Also the backend is similar. In the backend, once we identify a unit to replace lookup table, we put a hard microblock, we replace it, and we have the gate there. So the big question is that how this design is safe against various type of reverse engineering attack. When attacker doesn't know what the content of the lookup table is, how they can reverse engineer them. In academia, as well as industry, as well as Air Force Research Lab, they recently proposed a lot of theory-based reverse engineering solution. The most sophisticated one is SAT-based attack. This type of attack, essentially, they look at the circuit as a combinatorial, essentially, function, and they try in an iterative manner to identify in that combinatorial function what smaller module, lookup table in this case, we did hide. And by running it through the SAT solver iteratively, and removing all the min term and other function, they essentially try to get to the functionality of those lookup tables fairly quickly. And these solutions are really fast. Again, there's no time to go over the detail, how they work. But the big question here to answer is, in the solution that we propose to insert lookup table selectively in the design, where to insert this lookup table? How complex should be this lookup table? And also, how many input this lookup table should have? So these are the design questions that you need to address, and they're going to impact your design functionality at the end of the day, including your power, performance, area footprint, as well as the security. To summarize our results, what actually we've seen, we first look at various replacement policy. We developed several of them. Since 2016, we introduced a solution. We introduced several replacement policy. Also, other group in academia proposed several solutions. Here, I highlighted some of the most important ones. So from 2016 to 2019, we call them all heuristic-based solution. Meaning that as a designer, we look at the design, we identify, okay, which path in the design we are not using frequently, they don't show up in the testing, remove the primary input, primary output, some of the heuristic-based solution. And we put the lookup table in the places that we are not really seeing them frequently in various test methods. But as I said, these solutions are heuristic-based. They are based on some knowledge by expert designer. So looking at this heuristic-based solution from 2016 to 2019, and here we ran the latest SAT attack, 2019 version on this design. It shows some interesting results. That if we change the number of gates in the design for a simple 3,000 gate design, this is a test case, we only replace 200 of them with lookup table, obfuscate 200 of them with lookup table. The execution time in terms of reverse engineering it is not really significantly increasing as we increase the number of lookup tables in the design using this random policy. Now, looking at some more heuristic-based, some more smarter, where expert designer suggested it just increases the execution time slightly, although in exponential, but not really significantly, so we can call it infinite number. Then another heuristic policy similar, another heuristic policy similar, and so on and so forth. So what it essentially tells us is all of this heuristic policy that people have been developing over years, including what we've been developing, at the end of the day, they're not necessarily going to be in a multi-million connected gates. They're not going to guarantee security in terms of this sophisticated SAT attack. And also what we can see here is that just simply in a linear fashion, increasing the number of gates in the design that we want to replace with lookup table linearly is not going to make the design suddenly exponentially more difficult to reverse engineer. Because when we increase them in this case linearly, the increase here is also linearly. Here, only when we see exponential increase, that's where we can say the solution is effective. So far, the result I presented using heuristic-based solution are not really effective. The solution that actually we propose is to use some machine learning here. What is our machine learning? So first, we wanted to understand how we can guess the delay or the execution time of reverse engineering using machine learning solution. From the circuit, we extract several parameters. This is we need to initially run this circuit through this route to find whether our solution is SAT hard, or meaning that it's not possible to reverse engineering it, and this could take a very long time. So we extract several parameters from a circuit. We treat this problem as like a neural network problem. We extract parameters such as number of gates, complexity of gates, fan in, fan out, again, several parameters that designers, they use for optimization. And then we feed this information to a neural network for a given data set of a circuit and a given data set of a trained reverse engineered to find out whether we can guess this. And we actually spend about 6 months on this problem by manually collecting circuit feature. Circuit is a connected graph, whether we can guess the reverse engineering execution time. The longer it is, obviously, the better to prevent it from reverse engineering, right? So, and our solution essentially wasn't successful. Instead, what we did, we simply relied on convolutional neural network. And the beauty of convolutional neural network is all the features that normally we need to manually extract, a convolutional neural network automatically extract them through various layers of its network. There's a new, essentially, method in machine learning community, graph convolution neural network, where we are able to feed graph into a neural network. Many of us have heard of CNN, convolution neural network, where we can feed image to a neural network. Once, if this neural network is trained with a database of image, it potentially can classify the new incoming image with high accuracy. And the feature of the image are essentially extracted automatically by the convolutional neural network. Here is similar. Instead of feeding the neural network with an image, we feed it with a graph base. What is a graph? The circuit graph. So for that, we need to perform a lot of essentially translation of a graph to CNF to something else, to be able to prepare the graph, a bipartite graph, eventually, and feed it to the neural network. And this method showed that we can predict the SAT execution time. Using this method, we propose a method called cognitive obfuscation that is machine learning based. And in this method, essentially, with using graph convolutional neural network, we can navigate all possibilities of lookup table-based replacement policy in a design. Imagine you have 100 nodes in your circuit. What are how many possibilities you should explore? Trillions, because lookup table could be in 1 out of 100 location, 2 out of 100 location, 3 out of 100 location, all the way to 99 out of 100. Can you explore all of them? Not really. But with this method, we can explore all of them, and for each of them, estimate the execution time of the attack immediately. And potentially, that helps us to navigate the space fairly quickly to identify in this huge space, what is the best solution, where to insert this lookup table in this huge circuit to protect the circuit against reverse engineering. So this is a result for cognitive obfuscation solution that we had. And as you can see, for this particular circuit using the technique at 100 gate, we actually were able to make it SAT hard, or essentially unlimited. The execution time for SAT become infinite. This is just a layout showing the design that recently we taped out with TSMC, 65 nanometer, it's non-volatile logic base. It's a RISC-V, a dozen crypto engine, as well as 64 cores, neural network accelerator. We obfuscated all of them, and we have the test chip, and now we are essentially started performing the test. We have a red team that we're working, and they're going to reverse engineer design to see how much progress they can make in reverse engineering this design using our method. So this is essentially the first part of my talk. Sorry, I don't have watch with myself. How long more I have? 10 minutes? Okay, great. So let me go through the second part very quickly. I don't have many slides here, so hopefully these are some software-related security that has been around for many years. But now as a hardware, people in hardware community, we are essentially proposing an alternative solution for malware problem, side channel problem that has been around for many years, and cybersecurity community has been dealing to address this problem for many, many, many years. So malware, all of you familiar with the problem. Just show you some number, 2015 to 2017, McAfee reported, these are the new malware that they essentially collected. And the number are huge. Just 2016, they reported detection of 126 million new malware. In 2017, 140 million new malware. And just to put in perspective how big that number is, it is essentially 20 times more than number of applications that we have in App Store and Google Store. So we have a big problem here. Also today, Apple, as well as Google, they're dealing with this problem. A lot of software that they upload, a lot of application to release to the market. They do a lot of testing before releasing them. These two companies, Apple Market as well as Google. Google Market as well as Apple Store. However, after release, they release a patch, an update, or maybe they tunnel to a third-party software. And that way they can actually welcome malware to your cell phone. So this is a problem that even they're dealing with in the application level. So the solution that software community has had for many years was using antivirus. And these are great solutions. They're mostly relying on, they're signature-based, relying on signature of the software. However, when it comes to emerging devices in IoT domain, which they are really cheap in terms of economically building them, they don't have enough computational capability, they don't have enough storage also. We can't really put a full-blown antivirus from Norton or McAfee on those devices. We have only 4 kilobytes of memory. It's impossible to put gigabyte of a signature of a malware on those devices. So that's why I don't believe that the solution that we have in software domain eventually is going to make it on the edge node of IoT devices, which everything is small, tiny. We should be very conservative on power consumption, performance, memory footprint, cost. So the solution that I promote is to go back to the hardware. My main field essentially is computer architecture. And we're doing a lot of performance optimization over years, looking at processor architecture, collecting a lot of data from underlying processor microarchitecture, cache miss, memory miss, and so on and so forth. But we realize that these information, not only we can use them for performance tuning, but potentially we can use them to infer, to find an anomaly and to infer security. So here are essentially some interesting result figure showing two microarchitecture events that are happening underneath at the underlying microarchitecture of a processor. This is an Intel processor. And we collected a sample for some time. This is a malware, this is a normal program, benign program, and as you can see, there's a big difference between the two. So what essentially we proposed to the community was to use microprocessor. And these microprocessors are normally equipped with performance counter that we put on them for tuning. Google use them for the data center. Apple use them in their cell phone for running application. NVIDIA use them for even the GPU architecture. We use this for, but besides tuning performance, to collect data in real time and feed them to a classifier, a trained, well-trained machine learning classifier, to be able to infer anomaly. And I intentionally call it anomaly because anomaly for us means malware, Trojan, side channel, and many other malicious activity. So we propose a lot of solutions in this field. Again, there's not much time to go over the detail, but we identify several essentially challenges as well as the limitation in terms of number of monitoring knobs you have in processor. In your cell phone, you have only 2 monitoring knobs, whereas millions of events are happening at the same time. So the big question, out of these millions of events on your cell phone, which one you want to collect in real time every time you look at your cell phone application to eventually feed it to a machine learning classifier to collect information and classify it as a malware or non-malware. So we identify several interesting research problems here, address them as well. Again, there's not much time to go into the detail, but the interesting part here is Using our solution, which are ensemble learning, they can be also trained in real time. They're really low power. We can deploy them on a cell phone device, on IoT device. The prediction accuracy that we are seeing is essentially significant. So let me quickly go to the prediction accuracy result. So here are the numbers. We can essentially, with a database of thousands of malware and several hundreds of normal application, we can distinguish between malware and normal program with 98.1% accuracy. This is great. And this is essentially for malware that we have seen. However, we divide them into database as known, unknown. We perform all kind of a normalization, randomization. We do in machine learning theory. But this is not the end of the story. If we had this great solution, we could go and sell it to the industry and make millions of dollars. But the reality is the accuracy, when we're talking about the real-time, real scenario is significantly lower. And the real scenario happens when your normal program is embedded in your, or malware program is embedded into your normal program. This is what we call as a stealthy malware. What we assume here, or what many other researchers assume, is that malware is always spawned as a separate thread by the operating system. When operating system is running, it spawns multiple programs, right? It also spawns malware as a separate thread. So when we see it, we can collect information, we look at what we trained with our machine learning classifier, we compare, and then great, we have a malware. In reality, this is not what is happening. The malware could essentially be stealthy, could be embedded into normal program. And when we run that scenario, then the execution time, or the performance accuracy could drop significantly. And this is a result of 10,000 cases when we fired the malware in the middle of running a program, in a random time, in a random moment, in a random part of the memory. And the accuracy is all over the map, from 70% to 30%, using machine learning classifier when we collect all this information. So we essentially proposed several interesting solutions, very heavy-weighted solution that recently won the Best Paper Award at International Conference on Data Mining. And it also addresses stealthy malware and improved the performance to 90+% for even unseen malware, an unseen side channel. And again, you're welcome to look at the paper. The paper is also available online now. So let me actually conclude my talk with just going over some of the coolest stuff we are doing these days. And four main research that we're currently working on are, one, we're looking at how we can prevent malware epidemics in IoT network. Many of you have heard, may have heard of Mirai attack, recently reported. It happened in East Coast part of the United States. It infected a lot of IoT-based LAMP connected to the network. And our solution essentially is to also use machine learning classifier at the node level, collect runtime behavior, very lightweight version, then communicate in a coordinated manner with local node to be able to prevent epidemics in IoT network. We're also collaborating with a colleague of mine who's a control theory, and we have a machine learning solution, we have a control theory solution. Control theory always gives us the absolute best result. Machine learning always gives us the approximate result, but the advantage is that we are much faster than control theory-based solution. So this is essentially the advantage that we have. Also working on 3 other cool projects. One is hardening the RISC-V architecture. RISC-V, Samsung recently announced that they're going to make their next SoC using RISC architecture. The sci-fi company just across the street in Bay Area, they're developing RISC-V based architecture for mobile, for also server. We are essentially introducing RISC-V doesn't come with any security mechanism, no performance counter. We're introducing performance counter. We also had a fabrication on obfuscating RISC-V, preventing reverse engineering. This is we're continuing that effort. Another project we're looking at adversarial machine learning. One of my students started working on that about 6-7 months ago, more than actually that. We have some interesting result. And when you submit your job to Amazon AWS, as an end user, you want lowest cost, maximum performance. This is from user perspective. From Amazon perspective, Amazon wants guaranteed performance, highest cost, or some essentially better cost, let's call it. So what we did, we fired thousands, hundreds of thousands of jobs into Amazon AWS, collected various underlying microarchitecture information from this application. And we have the cost now. We have the server that we run the job, various server with various feature, Xeon server, E5, E3, E4, and so on and so forth. Then we try to build a cost model for, given the type of application we have, the server type we have, and the cost that incurred by Amazon. Once we have the cost, then potentially you can fool Amazon scheduler by embedding or wrapping another application into your program to change the behavior of your program to something else that Amazon or Google or other cloud sitting inside your university or your entity see as a normal, some application that really can run it very fast because they do all this statically, they don't really do it dynamically. Once you identify the cost model, you can reverse engineering it. You can fool it by inserting another program, wrapping it around your application. That way you can submit your application, you gain the same performance or similar performance, a little bit up and down, not the same similar performance, but the cost is going to be significantly lower. So this is essentially a very interesting work. We submitted it to SMP, the main conference in security. Another work is looking at meltdown spec rate. This is the work we started in 2016. We had 18 months publication restriction. We published several papers on that, how to detect this activity. So this brings me to the last 2 slides or 3 slides. I'm also working in a center. We are essentially, UC Davis is a part of 6 other universities across the country. University of Northeastern University, University of Virginia, University of Texas, Dallas, and University of Cincinnati, as well as University of Connecticut. And we are working closely with industry, as well as with AFRL, Air Force Research Lab in Dayton, Ohio, as well as with DARPA on challenging security-related problem. The center formed not long ago, very recently. The center is Industry University Cooperative Center. We have a large team of about 100 plus PhD students, several faculties, tens of faculties, and a lot of lab space research, all dedicated on hardware and cybersecurity problem. And we had the center meeting about a year ago, another meeting for funding. We had 6 member universities, 32 companies, several government research lab, and essentially a lot of my time also is taken to work with industry, bring a research project to university, and train, at the end of the day, workforce for industry. And with that, I conclude my talk, and thank you for your attention.
All right, I think we have time for a couple questions. Does anybody have one for our speaker? Yep, back there.
This is a good actually question. So digital circuit, we've been working on it for several years. And the good thing about digital circuit is that we're mostly using tool, standard design tool. There's a certain pattern we need to follow. If there's a breach in that pattern, we should be able potentially to catch it by using various methods. Analog are fully custom. So they're more difficult. This is, in general, a more challenging problem. The field very recently started, and I think there are a lot of opportunity also there to look at. But I think this is a more challenging problem in analog circuit, given the custom design nature of it.
Yes.
That's a very good one. So we tried actually feeding the features, but it didn't really work out. So we're actually feeding the entire circuit, but translated the circuit in a bipartite graph. And that's how we can, and into a graph neural network base. Yep.
Maybe one more? Yep, last one.
manufacturer figure out the design and change something that make it look like it's same but doesn't work the same way?
So about that particular video, I don't know, but they discover essentially that there's some malicious activity going on at the hardware level. And the chip that was deployed in some of these military and sensitive devices. But in general, if you let someone else to do the job for your chip, whether that job is testing, validation, fabrication, foundry, they have access to your design. And they can potentially put a bunch of transistors, and that's what they do. There are essentially, they're not reported cases of it, but they're potential. Potentially they can do it if it's a third party that you don't trust. By inserting few transistors here and there, and those transistors only fires at a time that, in a very rare cases, and that they don't really show up during the test process, and they essentially change the outcome of your circuit. It was for encrypting. Now, once those few transistors activate, it does something else that it's supposed not to do. And that's one essentially malicious outcome. Other could be the foundry, the third party could simply take your design and overproduce it. Instead of producing 1 million in XYZ country, they produce 1.5 million. We don't have camera inside, or there are cameras inside Foundry, but I don't think companies necessarily have agreement to go and see inside Foundry what is really happening. Some big player, TSMC, UMC, may not do it, but who knows about the smaller player? And these Foundry are several miles, essentially. They're big, there are a lot of robots